So, we start with chapter 2, determination of rate controlling step and estimation of overall rate of reaction. Our third chapter is actual process design, and what exactly is the role of this step, that I will explain you a little bit. What I am going to do while teaching this subject, I have already told you large number of multiphase reactions: gas liquid, solid liquid, liquid liquid, gas liquid solid, gas liquid liquid, gas liquid liquid solid. So, there are multiple combinations of multiphase systems. However, the fortunate part is the chapter 2, the way in which we learn and analyze any unknown system, the methodology does not depend upon the type of multiphase system. The methodology is generalized. So, what I am going to do is teach you the method for gas liquid system as a multiphase. However, by considering individual cases of liquid liquid, solid gas, then how the same methodology is applicable, I will describe to you. May not be at that time, there may not be a need to explain in as great detail as gas liquid, but you will realize, you will understand, you will appreciate that how the method is a generalized method, right. So, let us start with gas liquid, and let me give you two examples, right. And both the examples, both the reactors, since I have designed myself, I know all the intricacies. See, manufacture of hydrogen peroxide, you are still in third year, you have yet to undergo work practice. So, you might not have visited a factory manufacturing hydrogen peroxide. This hydrogen peroxide manufacture is also very interesting story, like self-inducing, but we do not have time for stories. Maybe I may tell here and there. This is ethyl naphthalene, which is hydrogenated, of course, in presence of catalyst. Please note, let us not lose the objective: determination of rate controlling step and estimation of overall reaction. That is the title, and whatever discussion has to happen, it should be focused only on this objective. There will be examples, there will be equipment, different equipment, there may be different operating conditions, but every discussion should end into further understanding of how to. So, what I am going to do is try to bring out to your attention why this step is required. So, one ring gets hydrogenated and then this is oxidized, and you get back C2H5 plus H2O2. This molecule, those who are unable to see, this is exactly the same as this molecule. So, hydrogenation, complete saturation, and which is oxidized. So, the hydrogen which goes and sits here gets oxidized, we get hydrogenation, and then ethyl benzene is recycled. So, ethyl naphthalene is basically a carrier. It gets hydrogenated, oxidized, and we get product. So, real reactants are hydrogen and oxygen, right? And ethyl naphthalene is. The story I'll tell you sometime later. What are the challenges in the design of hydrogenator and oxygenator? So, imagine a slurry bubble column where the catalyst powder and ethyl naphthalene is introduced at the bottom, and then we have hydrogen at inlet, and ethyl naphthalene also and slurry goes in, slurry goes out. So, what is done typically is we have like external loop airlift reactor, we have another pipe which gets connected here, and here sufficient area is provided in such a way, okay, ethyl naphthalene plus catalyst, that is a slurry which goes inside, all right, when we start the reactor. Then anyway reactor gets filled, the reaction is complete, we get this product, we have hydrogen in the form of bubbles. When it goes out, because of the settling of the catalyst settles in the external pipe and goes back to the system, and only the supernatant, which is this product, that really goes out for further oxidation. So, catalyst remains recycling in the system, what comes in is ethyl naphthalene, what goes out is the hydrogenated product, right. Now, when we pass hydrogen and there is a certain pressure, the hydrogen partial pressure at different locations. Similarly, the reactant which is 100% pure, say for example, at the inlet, and the outlet it is 99% conversion. So, the concentration keeps on changing from inlet to outlet. Take another reaction, say oxidation of acetaldehyde, the commercial process for making acetic acid or acetic anhydride. So, you pass air and acetaldehyde at one location, acetaldehyde gets completely converted to acetic acid or a mixture of acetic acid and anhydride. The point is aldehyde unreacted is not there. So, within the reactor, the aldehyde which is the major reactant, the concentration keeps on changing from highest at the inlet and keeps on decreasing everywhere in the reactor. Right? Take any liquid-liquid reaction, that is reaction of oil with water, hydrolysis to give fatty acids, very large liquid-liquid reaction. Take nitration of anything, chlorobenzene nitration, this is also liquid-liquid reaction. Right? So, within the reactor, if we take gas liquid, the gas fraction, the total pressure, the partial pressure, the liquid phase reactant, local temperature is likely to be different from place to place within the reactor. And if there is a capability with we chemical engineers that for every combination we are capable of finding rate controlling step at that point and able to write overall rate of reaction. Let there be many steps in the catalytic reaction, as you know, there is a absorption of hydrogen, then transfer of hydrogen from liquid phase to the solid surface, then there is internal diffusion, then on the surface there is a adsorption, there is a chemical reaction, there is a desorption of products which goes to liquid phase. So, out of all these steps for gas liquid solid catalytic reaction, which one is rate controlling, and if 2 are rate controlling, 3 are rate controlling, if all of them are participating in overall rate of reaction, depending upon local partial pressure, local hold up, local concentrations, local temperature, local pressure, how to write the overall rate at that point, so that in the total reactor I know rate here, I know rate here, I know rate here, I know at every point within the reactor, for every liter in the reactor I know how to write the rate. And if I integrate all those rates, it means I know the overall performance of the reactor. So, the process, what is the meaning of process design? We select any geometry for the reactor. Using step 2, we try to calculate the rates of reaction at every point, integrate them and see to it, confirm that the overall rate is in such a way that we get desired capacity, desired conversion, desired selectivity, right. So, therefore, these are the 2 steps in process design. In process design, we try to write overall rate of reaction at every point within the reactor, and in step 2, in chapter 2, we assume a generalized case that there can be anything, any multiphase, any controlling step, how to analyze such an unknown system that we study. So, that whenever there is known partial pressure and known parameters, we are capable of getting the overall rate of reaction. So, with this brief introduction, let me explain to you in great detail how it is done. I have already told you that I will explain for gas liquid, and I will not make generalized statement at the end that I have taught you gas liquid. Now, you learn liquid, liquid yourself, solid liquid, gas solid, etc. I will definitely explain to you individually for all multiphase systems, whatever we have learned for gas liquid, how it is applicable for each and every individual multiphase systems, right. So, learn gas liquid in great detail. If you have any difficulty, you can ask me. So, let us consider A plus Z times B is equal to products, and this is equation 1. Very good. If the order with respect to M, order with respect to A is M, with respect to B is N, then we write overall rate, which we have written before also, is equal to Kmn. Right now, I will write only A raised to M, and the liquid phase concentration is B into N. Whenever there is gas liquid dispersion, the gaseous component first of all is absorbed in the liquid phase and reaction occurs in the liquid phase. So, whenever we say reactor volume, I have said this before, but let me emphasize that reactor volume means the total volume of dispersion of gas liquid put together, right. However, the reaction occurs in the liquid phase. So, Kmn times A raised to m B raised to n, if this overall reaction rate is expressed in the form of kilomoles per meter cube second, which is happening in the liquid phase. So, this is per unit volume of liquid phase. So, if rate is to be expressed per unit volume of dispersion, then we multiply this by liquid fraction. So, in the reactor, if liquid fraction is 80% and on the basis of only liquid, the rate is say 1 kilomole per meter cube second. On the basis of total volume of dispersion, it is 0.8 kilomole per meter cube second. Understood? Of course, it is simple, it is very simple. We analyze all the multiphase reactions with the help of film theory. All right. You must have heard, but I am going to teach it again. What is assumed in film theory is the existence of thin film on the either side of interface, point number 1. Point number 2, this film is very thin and has uniform thickness throughout, point number 2. Point number 3, there is no convection or the flow within the film is 0, there is no convection and the entire transport in the film occurs because of only molecular diffusion. The 3 basic points of film theory. Would you like to write? Yeah. Should I write? Okay, then let me say, if required I will write also, this no issue. We are analyzing all multiphase reactions and the purpose is only one, the determination of rate controlling step and estimation of overall rate of reaction. For that aim, we analyze all multiphase reactions on the basis of film theory. Right? And film theory, there are 3 basic characteristic features of film theory. What it says? A thin film exists on the either side of interface, means if it is gas liquid, then there is a film on gas side, there is a film on liquid side. If it is liquid, there is a film on liquid side, there is a film on another liquid phase, insoluble liquid phase. If it is liquid solid and that is solid liquid interface, there cannot be a motion within the solid particles, and then in that case we have only liquid film and there is nothing like solid film, right, in case of gas liquid solid. So, a thin film exists. Initially I have said on the either side of interface, but in the fluid phase. Film exists only in the fluid phase, not in the solid phase. It has a constant thickness throughout. There is no convection inside. So, if you try to measure velocity at any point in the film, you get 0 velocity. And entire transport, let it be heat transport, mass transport, momentum transport, all the transports occur because of molecular motion, that is molecular diffusivity, molecular conductivity and molecular viscosity. So, in this I have explained to you with the help of the example of milk, how the transport occurs with the help of molecular motion, that is the random movement of molecules, they try to transport the momentum, mass and heat. So, this is equation 2. So, let me draw a film. And we are considering gas liquid. Therefore, on the either side means there is a gas film and then there is a liquid film. Whenever any transport occurs, then there will be some partial pressure in the bulk, there will be partial pressure at the interface, and then there will be a partial pressure in the liquid bulk. To begin with, let us make an important assumption which we will relieve towards the end, that there is no resistance offered by gas film. No resistance offered by gas film is an assumption. In reality, it may be there, it may not be there, but I am going to include it in the overall rate of reaction as we proceed further. So, for this partial pressure, so this partial pressure in the gas is denoted as P naught, and the saturation concentration at the interface is A star. There is another assumption, and which is a reality also. The interface gets instantaneously saturated with respect to solute gas. You might be knowing that 10⁸ molecules bombard on an area whatever is needle tip. On needle tip, 10⁸ molecules per second they bombard, and because of such high rate of bombardment, all the interfaces are instantaneously saturated. So, the interface concentration is A star, right. There is one extreme where no resistance is offered by the liquid phase, and the liquid phase concentration is also A star. Whereas, the liquid concentration is B naught. So, as you see here, the B naught I have taken it to be uniform in the film also is equal to the liquid phase concentration. So, if I take liquid phase concentration, now gas is getting dissolved going into the liquid, and the reaction is occurring between A star and B naught. With these notations, the same equation now I will rewrite with a small change, epsilon L K M N A star raised to M B naught raised to N, equation 3. This concentration profile is flat, or there is no resistance in the liquid film, whereas another extreme there is so much resistance in the liquid phase that the other end concentration A naught in the liquid phase is practically 0. There is a dissolution followed by chemical reaction. As the rate of chemical reaction increases, the dissolved concentration keeps on decreasing, and with very high rate of reaction, A naught is kept 0. In other words, as soon as the gas is dissolved, as it enters from the liquid film to the bulk, it reacts and A naught is kept at 0. and under these conditions it is completely mass transfer controlled, and we write RAA is equal to KLA into A star. If it is mass transfer, A star minus A 0. But when it is mass transfer controlled, A naught is 0, and therefore this is equal to really KLA into A star. So, equation 4 so this is equation 5. So, this is entirely mass transfer controlled, and if we increase the agitation in the equipment and try to increase the mass transfer coefficient, then the rate of dissolution becomes higher and higher, and there is a positive value of A naught. Keep on increasing the speed, keep on increasing the dissolution rate, and finally eventually if you increase the speed or increase KLA, eventually the solute concentration in liquid phase will reach saturation concentration. It obviously it cannot exceed that. So, when it is completely mass transfer controlled, entire resistance is provided by the liquid film, entire driving force occurs across the film, and liquid phase concentration of solute is 0. Whereas, when it is totally kinetically controlled and there is no mass transfer resistance, there is no concentration drop, and liquid phase concentration is A star, then it is called completely reaction controlled. Right? So, equation 3 is completely reaction controlled, whereas equation 5 is completely mass transfer controlled. So, then I can write it here, completely reaction control. Completely mass transfer. So, the value of A naught keeps on increasing as you increase KLA, right. So, what exactly we mean? if rate of mass transfer is much higher than rate of chemical reaction, then it is reaction controlled. If rate of reaction is much higher than rate of mass transfer, then we call it as mass transfer controlled. Now, much higher, for our purpose, we say that if it is 20 times higher, then it is much higher. Okay? For our purpose, that is sufficient. So, if these are the two rates, and if we say that this rate is much higher than this, that is, if KLA is much greater than epsilon L Kmn star raised to m minus 1 B naught raised to n. If this is much less, here there was KLA A star, here it was A star raised to m. So, I have taken away one A star and written m minus 1. So, when this rate is much higher than whatever I have written on right hand side, then this is called reaction controlled. And if KLA is much less than I have already told you, 20 times is much less, is epsilon L Kmn A star raised to m minus 1 B naught raised to n. And we call it as mass transfer control. There is a possibility that both the conditions are not satisfied. So, some resistance is provided mass transfer, some is provided by chemical reaction. So, suppose I combine both the equations, let me give this as number 6 and number 7, and this is not satisfied, this is not satisfied, or both are comparable, then I can always write A star upon RAA is equal to 1 upon KLA plus 1 upon epsilon L Kmn A star raised to m minus 1 B naught raised to n. So, imagine KLA is much greater than this, KLA is much greater than this. In other words, 1 upon KLA is much less than this. So, this cancels and we get RAA is equal to epsilon L Kmn A star raised to m B naught raised to n, which is our equation 3, which means it is completely reaction controlled. If KLA is much less than this, 1 upon KLA is definitely much greater than this is negligible, and RAA is equal to KLA into A star, that is equation 5, and it is mass transfer controlled. Understood? Yes? Yeah. So, what I have done, the title of the chapter is Determination of Rate Controlling Step, Estimation of Overall Rate of Reaction. We have just started. I have told you mass transfer controlled and how to write the rate. Reaction controlled, I have told you how to write the rate, and I have told you how to write overall rate of reaction if both are participating in the overall rate. So, I have combined both the rates together, so that for any possibility in between we can write overall rate of reaction. Up till now no problem? Okay. Now, let me move further. So, this is, let us give another number 8. Now, in both the cases, we have made one very important assumption, which we will write now. While writing equations 2 to 8, we have assumed that no reaction occurs in the film, right. A enters the bulk liquid and there it reacts. Either it completely reacts and A0 becomes 0, or the rate is so high that it remains is equal to saturation concentration, but reaction occurs in the bulk. Yeah, right. Something it should be RAA upon A star. Suppose I write like this. Is this okay? Good, 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 good. Thank you. So, when reaction happens in the film, there is a possibility always that something will happen in the film and something will happen in the bulk, correct, no? So, let me teach you first of all what happens if complete reaction happens in the film, and then we will go back if part of it occurs in the bulk. Right. So, in the liquid film at the interface, the concentration is A star and the reaction happens in the film, and before it ends meets the other side of the film, nothing enters into, now A0 is equal to 0. Now, I wrote A0 is equal to 0 earlier also, but the meaning there was all A was entering into liquid bulk, and because of the fast chemical reaction A0 was maintained to be 0. Whereas, in this case all the A reacts in the film and there is no A available for entering into liquid bulk, and therefore, A0 is equal to 0. And this can happen only if at this point dA, suppose this dimension is x, dA by dx is equal to 0. Slope is also 0 and A0 is also 0. Then all the reaction happens in the film. It does not enter the bulk means slope is 0, and its value is equal to 0 means anyway it is completely reacted, right. I am writing B0 to be constant. Earlier also I considered B0 to be constant in the entire film, but I need to explain to you there are conditions under which this will happen, and there are some conditions under which this will not happen, right. Now, let us analyze this case. It is completely all the reaction happens in the film. How do we analyze this? Take a small differential element, which is at a location x with a very small thickness dx. So, A enters this surface by diffusion, leaves this the other end of dx by diffusion, and some chemical reaction happens here. And some chemical reaction when added for all the delta excess in the film, the reaction is complete. So, let me write the mass balance. Rate of input of A minus rate of output of A minus rate of chemical reaction this is complete mass balance is equal to 0, and we are writing mass balance for component A, the gas phase species in the liquid film. So, what enters inside is the diffusivity into dA by dx. This is how we write the flux, what enters inside. So, multiplied by the cross section, which is, say I write S at x minus diffusivity dA by dx at x plus dx minus chemical reaction Kmn. Locally concentration is A raised to m, and concentration of B is B naught at this location also. So, B naught raised to n. So, this reaction is occurring in the differential volume multiplied by S dx. This reaction is kilomoles per meter cube second multiplied by meter cube of that differential volume is equal to 0. We divide throughout by S dx and take limit tending to 0, and we get diffusivity d2A by dx square is equal to Kmn A raised to m B naught raised to n. We had come up to 9 earlier. This itself is 9. Okay. Now, this equation we want to solve, but boundary conditions are known to us. At x is equal to delta, other end of the film, A is equal to 0 and dA by dx is also 0. And at x is equal to 0, the specific rate kilomoles per meter square per second is minus diffusivity times dA by dx at x is equal to 0. So, when Fick's law is applied at x is equal to 0, whatever flux happens, that is kilomoles per meter square second, multiplied by interfacial area gives kilomoles per meter cube second. Now, let us try to solve. Let us assume dA by dx is equal to some variable p. So, the left hand side we can write p dp by dA is equal to Kmn upon dA a raised to m b naught raised to n. Have you understood this? What has been done is d2 a by dx. So, dA by dx, this has been split in such a way that so, this dA can cancel with each other and dP by dx, since P itself is dA by dx, dP by dx is d2A upon dx square. Is that right? No, it's okay. So, let me do integration p dp is equal to Kmn upon dA this is one of the simple b naught raised to n into dA. What is the integration of left hand side? P dP? Yeah. So, let us do integration. So, P dP is p square upon 2, a raised to m, this is getting integrated. So, a dA, a raised to m dA, what is the integration? So, Kmn upon dA a raised to m plus 1 divided by m plus 1 b naught raised to n. Understood? Plus integration constant, plus integration constant. What is the boundary condition we have? At x is equal to delta, the slope, anyway, let us take, we can take this further. P itself is dA by dx. So, at x is equal to delta, A is 0 and dA by dx is also 0, and therefore, C is 0. So, at x is equal to delta, P is 0, A is 0, and therefore, C is 0. Therefore, P square by 2 is equal to 1 upon m plus 1 k m n a star raised to a raised to m plus 1 b naught raised to n divided by diffusivity. R P is equal to 2 upon m plus 1 k m n upon diffusivity of A raised to m plus 1 b naught raised to n. What is the other boundary condition we wrote? At x is equal to, this is of course is equal to then square root of this, and then the answer is plus minus square root. Are you with me? Right. So, at x is equal to 0, R A is equal to minus diffusivity times dA by dx, obviously at x is equal to 0. Therefore, R A is equal to minus diffusivity times P, which is equal to now minus plus 2 upon m plus 1 diffusivity k m n. Similarly, at x is equal to 0, A is equal to A star, which is saturation concentration. We are talking about all the reaction happening in the film, and at x is equal to 0, A is A star, and the slope multiplied by diffusivity is the. So, now we write A star raised to m plus 1 and B naught raised to n. So, let me give some equation numbers. We will call this as 10 plus C, we will call this as 11, call this as 12, and R A is equal to as 13. We have earlier seen mass transfer controlled and reaction controlled. Mass transfer controlled is KLA into A star. That is very simple. Is that equation number 5? KLA into A star, correct? So, when it is mass transfer controlled, it is called basic rate, and whenever reaction happens in the film, enhancement happens over and above the mass transfer rate. So, enhancement factor, if you want to write as phi is equal to enhancement factor then this is R A when it is mass transfer controlled, and then numerator is R A, the actual R A. If I want this to be converted into RAA, then I can always write RAA is equal to A star RAA is AA star 2 upon m plus 1 dA Kmn S star raised to m minus 1 B naught raised to n. So, I can always phi write like this, or I can write like this. And if I name this also as equation 14, then phi will become I am not writing intermediate step because I am this divided by equation 5 when mass transfer controlled. So, phi is equal to this divided by KLA into A star. So, this A star will vanish, this A will vanish, and enhancement factor phi is equal to 2 upon m plus 1 dA Kmn A star raised to m minus 1 B naught raised to n divided by KL. Okay. Let us give some equation number. This is 15. You have not realized one thing, that is chapter 2 is complete. Now, I am going to teach for good number of hours chapter 2, but essentially it is complete. Whatever discussion now onwards will follow, some derivations will be there, small derivations which I will do, but what is mass transfer control, what is reaction control, what is the meaning of completely film reaction controlled, and how do we write the enhancement factor. We have made up till now one assumption that B naught remains constant in the film, which we will have to remove next time. So, we will meet tomorrow at 4:30.